Good morning. This is your stats sensei, Mr. Spensei, and we're going to go over inferences. We're going to start with means. We're going to work our way through proportions, then chi-squared, and then regression. This will be quite a bit of material covered. I will say that it does not have types of errors, power, and so types of errors, power, and p-values are not covered on this in this group. That's because it got so long. So an environmental group conducted a study to, and this is a 2013 question one, an environmental group conducted a study to determine whether crows in a certain region were ingesting food containing unhealthy levels of lead. Our biologists classified lead levels greater than 6 parts per million as unhealthy. That's important. The lead levels of a random sample of 23 crows in the region were measured and recorded. So here we have 23 readings. It's in a stem plot. Please remember, this is 28, this is 30, this is 35, 38, etc. What proportion of the crows in the stem plot had lead levels that are classified as unhealthy? Well, they said anything greater than 6. Well, in this case, it looks like I have 4 out of 23. As a matter of fact, if I showed the fraction and then turned it to a decimal, that's all I needed to do in order to receive full credit right there. Okay, so the mean level of lead of the 23 crows in the sample is 4.9, and the standard deviation was 1.12. And this, by the way, this is from the sample, so this is S, and this is X bar. Construct and interpret a 95% confidence interval for the mean level of crows in the region. So please understand that when we're calculating confidence intervals, is because we don't know the population mean and we're trying to find an estimate. So let mu equal the true population mean level of lead in crows. Make sure that you have all of that so that it's in context. Conditions. Random sample of 23, that was given. 23 times 10, I'm pretty sure that there's at least 230 crows, so the sample size is less than 10% of the population. I also need to check normality, but they did me a favor. They gave me a graph, and when I look at the graph, I'm like, reasonably symmetric in mound shape, no outliers. So the stem plot is reasonably symmetric with no outliers. The data appears normal enough. So it looks like the normality condition is taken care of. So I need to run a one sample t interval for means. It's very important that you name your tests, all right? And or one sample confidence interval, t confidence interval for means. Make sure that you put the word t or z if it's a z. And remember, the difference between a t is a t uses the standard deviation of the sample, which is what we had up here, and a z uses the standard deviation of the population. So here's my formula, x bar plus or minus t star s divided by the square root of n. Now we want to cross that out in case we make an error. Now they told me my sample mean was 4.9, plus we'll come back and we'll figure out t star in a moment. The standard deviation is 1.12, and 23 was my sample size. Remember, all we're doing is saying, hey, you know what? The standard deviation of x bar is the standard deviation divided by the square root of n. If it had been a population, we would have done standard deviation of x bar is the standard deviation divided by the square root of n. But in this case, we're working with the sample, so this is what we have. All right, so I need to get that t star value. So second vars, inverse t, the area, because it's a confidence interval, we have to subtract and divide by 2. So 1 minus 0.95, close parenthesis, divided by 2. And degrees of freedom in this case are n minus 1, so 23 minus 1. Make sure for confidence intervals that you write it down. So I make a habit of writing down my degrees of freedom all the time. So I have 2.0738. So there's my, that's my plug-in values. Now I need to go ahead and run the test. So I go stat test. And I'm going to drop down till t interval. Oops, too far. No, it's not too far. So here we go. 8 at t interval. And I have statistics. I need to plug those in. And the x bar was 4.9. Standard deviation is 1.12. The sample size was 23. And I need to calculate a 95%, so 0.95. And I end up getting 4.4157 to 5.3843. All right, so there's my interval. And we are 95% confident that the true population mean level of lead and crows lies within this interval. So we're confident that somewhere in there is where the true population mean is. It could be on the low side, it could be on the high side, but we're pretty confident that it lies in there. In repeated samplings, we expect that this method will capture the true population mean level of lead in crows 95% of the time. Now, this is the definition of the confidence level, which isn't required unless they ask for it, but you always have to provide this. Also, if you notice, 6 isn't in here, so we don't think that on average we have crows that have too much lead. We just have a few that have too much lead. We know we have 4 that do, but as a part of the population, it's like, no, the lead level is below 6, so we can't say that it's unhealthy. On average, we cannot say that it's healthy based on this sample. All right, so one thing is they don't run a whole lot of hypothesis tests for one sample teas. One sample teas are considered relatively easy, and so they usually cover that in a question 6 if they're going to cover it at all, and so that they can make it a lot more challenging when they do so. So here they put one in question 6. So we're going to capture a bunch of things in this problem. Matter of fact, we're going to capture one sample T, a paired T, which is a special case of one sample T, and we're actually going to capture a little bit of regression, all in this question 6. So this is 1999, question 6. Researchers wanted to see whether training increases the capability of people. You know what? I'm going to pause this thing right here and end that last video.